Today we're going to continue on with Big Idea 8, Standard 2, Factors that Increase Reaction Rate. So at the end of the last lesson, we said in order to increase reaction rate, there needs to be more successful collisions. Don't mind my dog. So let's say I had reactant A and reactant B, and we wanted to join them together to make compound AB. Well, in order for that to happen, A needs to collide with B. The more collisions we have, the faster that reaction is going to occur. So the first way that we can increase reaction rate is by increasing the pressure or decreasing the volume. This is always going to be an inverse relationship. So if pressure goes up, volume goes down. If pressure goes down, volume goes up. The reason why increasing the pressure or decreasing the volume will increase reaction rate is because the molecules will be closer together, which means they are more likely to collide. This is going to be for gases only. So let's say I had a gas like hydrogen, H2, and let's say these are all of my hydrogen molecules, and we are going to increase the pressure on these molecules or decrease the volume. So if we decrease the volume, now my space is much smaller, which means those molecules are closer together. If those molecules are closer together, they're more likely to collide. And we said the more collisions we have, the faster the reaction is going to occur. Factor 2, we can increase concentration. If we increase concentration, there's more reactant molecules available for collisions. We can increase the concentration of aqueous solutions. So let's say I had like a 1 molar solution of hydrochloric acid. And let's just pretend that was my 1 molar solution. And now I can increase the concentration. Well, that means I'm going to have more moles in the same amount of volume. Let's say I went up to a 2 molar solution. My concentration doubles. I'm going to have twice as many molecules. So I have more molecules in the same amount of space, which means they're closer together. The closer those molecules are, the more likely they are to collide. The more collisions we have, the faster the reaction will be. Factor 3, we can increase temperature. So we should know bullet point A already from Big Idea 7. As temperature increases, kinetic energy increases. So we saw that when we were doing our heating and cooling curve calculations. Anytime we had an increase in temperature, we had an increase in kinetic energy. So as temperature increases, kinetic energy increases as well. Remember what kinetic energy is. This is the energy of motion. So if kinetic energy is increasing, molecules are moving faster. The faster the molecules move, the more likely they are to collide with enough energy to reach activation. Remember our potential energy diagrams. In order for a reaction to occur, we have to make sure we put in enough energy for it to reach the activation energy. Factor 4, increase the surface area. If we were to increase the surface area, it exposes more places for collisions to occur. This is for solids only. So let's say I had a whole strip of magnesium ribbon. Well, in order for the magnesium to react, there needs to be collisions. Well, only those magnesium atoms that are on the surface are available for collisions. All of these magnesium atoms in the middle are insulated. They're not able to react because they're not exposed. So let's say we were to increase the surface area. What we can do is cut that piece of magnesium into a bunch of small little pieces. So before, only those atoms on the very perimeter were able to react. Well, now we expose a lot more surface area. The more surface area we have, the more collisions we can have. The more collisions we have, the faster that reaction is going to occur. Lastly, we can add a catalyst. So what a catalyst does is it increases the rate of reaction by providing an alternate pathway with lower activation energy. Let's say you had to mow an acre of grass and you used a push mower. Well, that's going to take a lot of energy pushing that lawnmower over the full acre of grass. It's going to take a lot of energy. It's going to take you a long time to do it. Let's say we had an alternate way for you to do the same job that took less energy, like a riding lawnmower. If you use a riding lawnmower, it's going to take less energy. If it takes less energy, you're going to get that job done much quicker. That's what our catalyst does. It provides an alternate pathway with lower activation energy. So let's say this was my reaction. Without a catalyst. So the activation energy is how much energy does it take to get from the reactants up to that activated complex. We have to push that mower all the way up and over the hill. Let's say we had an alternate pathway that took less energy. Well, the less energy that it takes, the faster that reaction is going to occur. So my blue line represents what this reaction would look like with a catalyst. The other important thing to note about a catalyst is that it can be regenerated. So the catalyst doesn't actually participate in the chemical reaction. It doesn't change the products. It remains chemically unchanged at the end of the reaction. So that means if you put in 2 grams of a catalyst, you can get 2 grams back out at the end. It can be regenerated.